Welcome back to the video course on fluid mechanics. In the last lecture we were discussing about the dynamics of fluid flow. So, in this we have already discussed about the objectives of this topic, dynamics of fluid flow, and then we have seen the various aspects of the dynamics of fluids flow, which we will be discussing, like analysis of fluids in motion. Say we have already seen the fluid kinematics say without considering the various forces. So, but in dynamics of fluid flows we have seen we will be discussing the various fluid motion including whenever forces are applied. So, some introductory aspects we have seen various cases which we will be discussing, and then we have also seen various forces influencing the fluid motions, like gravity force, fluid pressure, force due to molecular viscosity, surface tension, compressibility, Reynolds stresses, etc. And then also, as we have seen, that fluid motion can be either one dimension, 2 dimension, 3 dimensions, or a steady state and transient, or the uniform flow, non-uniform flow with respect to dynamics of fluid flow also. And then we have also seen the various aspects, like say how to analyze when we are analyzing the fluid flow. Say we will be either using a specific say we will be using endless stream of fluid, so that what part of this stream shall constitute the system which we will be analyzing. So, we have seen two alternatives. One is behavior of a specific element of fluid of fixed mass, so in a closed system. So, there are two alternatives, the way of analyzing fluid flow. First one is behavior of a specific element of fluid of fixed mass in a closed system, and then we can also do the analysis by defining a system as a fixed region in space known as control volume, through which a fluid floats, so that it is an open system. So, this we have seen, and now in our analysis we will be using this finite control volume analysis, as we have discussed in the last lecture. So, this finite control volume analysis used in many of the theoretical development in fluid mechanics, including this dynamics of fluid flow. So, the advantages are it is very easy to interpret physically and use, and then the formulas derived from basic we can apply basic laws, we can apply to the system, and say as we have seen the discussion how we are dealing the fluid flow is concerned, it can be either say Lagrangian description or Eulerian description, but in this say final control volume analysis we will be using the Eulerian description, and then the basic is the basic development is based upon the Reynolds transport theorem, which we discussed earlier in the fundamental aspects of fluid mechanics in the earlier lectures. So, now in today's lecture we will derive some of the fundamental equations, say starting from the conservation of linear momentum. So, first we will derive the Euler's equation for inviscid flow or non-viscous flow, and then also we will discuss the Bernoulli's equation and its applications. So, as far as the three fundamental principles of fluid the principles based upon the most of the theories are derived, we have already seen the conservation of mass, based upon which the continuity equation is derived, that we have already seen in the previous lectures, how to derive the continuity equation based upon the conservation of mass. So, one says this is one of the other most important say theory based upon which the most of the fundamental laws are derived is conservation of linear momentum. So, today we will derive the Euler's equation based upon this conservation of linear momentum, and then further we will derive the Bernoulli's equation based upon the Euler's equation. So, say as the word itself indicates, the conservation of linear momentum means the title itself indicates the linear momentum is conserved. So, what is momentum? So, we all of us know that momentum is the quantity of motion an object has. If the object is in motion, then say it has momentum. So, a momentum can be defined as it is a quantity of motion an object has, say when the object is in motion. So, then we say that it has momentum. So, the momentum, of course, say most of the bodies are the moving bodies have got mass and then it has got velocities. So the momentum basically depends upon the mass and velocity, so that we can express the momentum as mass multiplied by the velocity. So here you can see that the momentum depends upon mass and velocity, and then we can express the momentum is equal to mass into velocity. And then say a body under motion, say fluid in motion, then an impulse is, we can say that an impulse is exerted on an object which is in motion when the force acting on the object is a force is acted upon the object, so that we can say that the impulse which gets to the object is proportional to the force. So impulse is also very important as far as the momentum of the system is concerned, linear momentum of the system is concerned. So the impulse depends upon the time that the force acts upon the body or upon the fluid which we are considering, so that we can say that impulse is directly proportional to time. So that here as written in the slide, we can write impulse is proportional to force into is equal to force into time, so that impulse is directly proportional to time. So the momentum is depends upon the impulse, so that when we discuss the consideration of linear momentum, we have to consider an impulse, that means force applied with respect to time, and then what with respect to the motion, already it has the body or the fluid has already a momentum. So both this will be playing as far as total momentum is concerned. So the impulse exerted on an object is equal to the object's change in momentum. So finally we can define the impulse as the impulse is the what is exerted, impulse is exerted on an object is equals the object's change in momentum. So it is, say, whenever already a fluid is moving, so that we can say that with respect to the motion, say there is already a initial momentum, and then we are applying an extra force on the fluid or on the particle which you are considering, so that there is a change in momentum. So this is so called impulse of the with respect to the force which is acting upon the fluid or the body which you are considering. So we will say that if no impulse is exerted on an object, then momentum of the object will not change. So these are all some fundamentals of this say mechanics, so based upon which also the fluid mechanics theories are derived. So we can say that whenever say there is no impulse, then we can say that the momentum is not changing, momentum is constant. So that means this leads to the conservation of momentum. So according to the conservation of momentum, we can say that final momentum is equal to the impulse which is acted upon the body or the fluid which we are considering, and then plus the initial momentum. So the bodies or the fluid which is under motion, it has got an initial momentum. So then the final momentum will be, if we are exert an extra impulse, so that there is a change in momentum. So the final momentum will be impulse plus the initial momentum. So while we consider the conservation of linear momentum, we have to see that what is the initial momentum for the fluid or for the body which we are considering, or then what is the then what is the change, or what is the impulse acted upon the body, so that the total or the final momentum is equal to impulse plus the initial momentum. So now say as far as any fluid system which we discuss is concerned, if there is no external force act on a system, then we can say that the total momentum of the system will not change. So we have already seen that the total momentum is equal to initial momentum plus the momentum change due to the impulse, so that we can say that if there is no external force act on a system, then the total momentum of the system will not change. So such a system is called an isolated system. So the system can be of two types, wherever there is the total momentum of the system is not changing, so that there is no external force, what the fluid is moving or the body is moving with its own that initial momentum, so that we can say that the total momentum is not changing, so that such a system is called a isolated system. And the other type of system is whenever we are exerting force, so that there is an impulse and then there is a change change in momentum, so that the normal say whenever when we consider the dynamics of fluids flow, most of the time we will be discussing due to external forces acting with respect to the system, but sometimes also depending upon the problem isolated system will be also considered. So that finally we can say that the Euler's equation which we are going to derive is based upon the conservation of linear momentum. So the momentum is so we can say that when we consider a particular control volume, say we can say that the momentum is conserved in a very isolated system. If you isolate a system and if there is no external force, then we can say that the momentum is conserved in that particular system. But as far as the internal forces are concerned, it can never change the total momentum of a system, even though there can be internal forces within the fluid system which we are considering, but it cannot change the total moment of a system. So these are some of the fundamentals as far as when we consider the linear momentum and the impulse or the effect of force upon a particular system. So system can be either isolated system or the system can be wherever an impulse is acted and then there is a change in momentum. So and we have seen that if the internal forces are concerned, it cannot change the total moment of a system. So now based upon this say the linear momentum equation we can write here as shown in this slide here. Say if F is equal to, if F is the resultant force acting on a fluid mass, F is equal to dP by dt, where P is the linear momentum. So the force is equal to say the total derivative of this linear momentum with respect to time. So F is equal to dP by dt or for that particular system, or we can write the momentum is equal to so the integral of this V dm. So this is the basic definition when we consider the linear momentum equation. And for a differential system of mass, say with a mass of delta m, we can write delta F is equal to V the total derivative of V into delta m, so that this is the velocity multiplied by the small mass delta m. So here in this equation P is equal to integral for the system V dm, where V now delta F say for a differential system of mass which we will be generally considering while deriving the equation. So delta F is equal to the d by dt of V delta m as written here, so that we can write delta F is equal to delta m is constant, so delta m can be taken out, delta m dV by dt. But here you can see that this V is the velocity and then dV by dt is the acceleration A of the element which we are considering here. So finally now with respect to this we know that from a Newton's second law this force is equal to mass into acceleration. So this delta F also we can write as delta m into a. So that means effectively the change in force or delta F is equal to the mass into acceleration, that is what we are getting with respect to the equations here. So now if you consider the resultant force acting on a fluid mass, so here we consider, as in this slide we consider fluid element here of say small area delta A, and here this with respect to x, y, z axis. So say the forces acting can be put as delta Fs is split in delta F1 and delta F2, and then delta Fa with respect to normal. So the arbitrary surface which you are considering. So the resultant force acting on fluid mass is equal to the time rate of change of linear momentum of mass. So with respect to the conservation of linear momentum, we can say now in the previous slide we have already seen here, so that say the delta F which we derived is equal to d into d by dt of V dm, or delta F is equal to delta m into dV by dt. Again that comes as the mass into acceleration of Newton's second law, delta m into a. So from this we can say we can consider here the resultant force acting on the fluid mass as shown in this figure is equal to the time rate of change of linear momentum of mass. So finally with respect to the consideration of linear momentum, say now also considering the Newton's second law, we can write the resultant force acting on fluid mass is equal to the time rate of change of linear moment of mass. So now, as in this figure, we consider a mass of delta m, and as far as this figure is concerned, here various kinds of forces will be acting on this particular fluid element of mass which we are considering. So this is the fluid element which we are considering. So the forces generally are the surface forces and the body forces. So the body forces is concerned, here you can see with respect to this figure, delta fb is say with respect to this particular fluid element which we are considering. So the body force is mainly used to due to the acceleration due to gravity, so that we can write delta fb is equal to delta m into g, where g is the acceleration due to gravity and delta m is the small mass which we are considering. So this is the body force, so for this particular fluid element. So now based upon this, we are now in the process of deriving the Euler's equation. So before that, we are now seeing for a particular fluid element which we are considering when we derive these kinds of fundamental equation, we are considering fluid element of mass delta m, and then we are now checking what are the various forces acting upon that on that particular fluid element. So now the surface forces can be either normal to the surface which you are considering, or it can be also with respect to the shearing stresses. So here if we consider the normal stress with respect to the previous figure, here if we consider this particular fluid element, the normal stresses can be say we can write sigma n is equal to, when the limit delta a approaches to 0, this can be written as delta fn by delta a. So the normal stress is equal to the delta fn by delta a when the limit delta a approaches to 0 with respect to this previous figure here. So now the other surface force is so called shearing stresses. So the shearing stresses we can write as say as shown in this figure, it can be split into say with respect to these forces F1 in this direction and F2 the other direction. So F1 in this x direction, F2 in the y direction. So if you consider that, then we will be having two components for the shearing stresses. So these components are, first one is tau 1. Tau 1 is when limit of delta F1 by delta A as delta A approaches to 0, and tau 2 can be written as limit delta F2 by delta A at as delta A approaches 0. So these are the main surface forces. So we have already seen, say as far as a fluid element is concerned, the important forces are the body forces. So that body forces with respect to mainly due to acceleration due to gravity, as we have seen here, the body force is delta Fb is equal to delta m into g, and then the surface forces are concerned, there can be normal and shearing stresses. Normal stress we can write with respect to the normal force. So here sigma n is equal to delta fn by delta a as limit delta a approaches to 0. So similarly shearing stresses tau 1 and tau 2, we have already say here the expression for tau 1 and tau 2. So now by using all these the consideration of based upon consideration of linear momentum, we are going to derive the one of the fundamental equation of say fluid mechanics, so called Euler's equation. So this is mainly for inviscid flow, that means flow is considered without the viscosity. So that is will be derived based upon the consideration of linear momentum. So now to derive this Euler's equation, let us first consider a fluid element like this of size delta x, delta y, delta z. So as shown in this figure, the fluid element is considered. So for the fluid element, the forces acting, let us consider now the x direction. So x is in this direction, y is this direction, and z is the other direction. So the various forces acting here, you can see that as we have seen the earlier the two types of forces, we have seen the surface forces and the body forces. So the surface forces we have already seen, it can be the normal stress with respect to normal stress or shear stress. So here with respect to the normal stress, so for this particular fluid element we can see that here for this in this direction on this face of the fluid element it can be written as, since the x direction is like this, so on this face it can be written as sigma xs minus del sigma xs by del x into delta x by 2 multiplied by this the area of this face of the fluid element delta by delta z. And then similarly the opposite side of this other side of the fluid element we can write here the normal with respect to normal stress the force can be, the surface force can be written as sigma xs plus del sigma xs by delta x into delta x by 2 into delta y delta z. So this is as far as the normal stress is concerned. And now we have also seen there will be body, there will be the surface forces with respect to the shear stress. So here if the shearing with respect to the shearing is concerned, say the shearing stress is concerned, we can write on this face as tau yx minus delta tau yx by del y delta say delta y by 2 in delta x in delta z. So similarly the other direction to be tau yx minus del tau yx del z by del z by 2 in this direction, and here the other direction is tau yx plus del tau yx by del y and delta y by 2 delta x and delta z. So similarly other phase also we can, so all the phases we can write the body forces as far as this particular fluid element is we can write the surface forces for this particular fluid element is concerned. One is with respect to the surface forces with respect to the normal stress on this face and other face, and similarly the shearing stress is concerned we can write all the components. So now with respect to the surface forces, say if you take the ijk, that means the xyz direction, we can write this total say surface force delta fs is equal to del phi fsx I with respect to the ijk triad, the unit vector I, plus delta f sy j plus delta f is sez k. So now we have seen that this particular fluid element which you consider there are three components x, y, z. So for the surface force we have seen. So now if we consider in the x direction with respect to the previous figure, this figure we can write delta fs is x equal to delta fs is equal to delta sigma xs by delta x plus del tau yx by delta del y plus del tau z by del z into delta x del y del z. So this is the body the surface force with respect to the normal stress and shearing stress. So similarly delta fsy can be written as del tau xy by del x plus del sigma yy by del y plus del tau zy by del z into delta x delta y delta z. And similarly in the z component we can write del f sez is equal to del tau xz by del x plus del tau yz by del y plus del sigma z by del z into delta x del y del z. So now with respect to the fluid element we have seen the three components with respect to x, y, z direction of the surface forces. So now as we have seen the total forces are concerned, there is surface forces and body force. So the body forces, as I mentioned, we will be, it will be with respect to the acceleration due to gravity. So this also we can put in x, y, z direction. So here the body force are concerned, del f bx in the x direction will be mass into acceleration due to gravity in x direction. So delta m into gx, and in y direction delta f by is equal to delta m into gy, and delta f bz is equal to delta m into gz. So this is these are the body force component in x, y, z direction. So now with respect to the Newton's second law, we have seen, also we have seen earlier with respect to the conservation of linear momentum. So finally we have come to that if you use the Newton's second law, we will be getting effectively this conservation of linear momentum. So now the various forces we have seen for the particular fluid element, the surface force and body forces. We have already seen various components of the surface forces, and also we have seen the various components of the body forces. So now as per the Newton's second law, in x, y, z direction, we can write delta fx equal to, that means the force in x direction is equal to delta m into acceleration in x direction, and delta fy is equal to delta m into ay, and delta fz is equal to delta m into az. So where delta m is the mass of the fluid element, so if rho is the density of the fluid element, so we can write delta m is equal to rho into delta x into delta y into delta z. So now all these parameters are known. So now if you use the Newton's second law, finally we can write the general differential equation of motion for the fluid in x, y, z direction. So by using Newton's second law, we have equated the forces to the mass into acceleration. So the forces are concerned, we have seen the body forces and surface forces. So by using Newton's second law, if you equate, then we can see that this in x direction the equation will be rho gx, which is the body force in x direction, plus due to the stress force, shearing and normal stress, we can write del sigma xs by delta x plus del tau yx by del y plus del tau zx by del z is equal to mass into acceleration. So mass is we have already seen say rho into delta x and delta y and delta z. So this delta x, delta y, delta z are there in all these components which we have derived. So delta m has got a delta x, delta y, delta z, and also we have seen delta fsx, delta fsy, delta fsz, all these have delta x, delta y, delta z. So while using the Newton's second law and equating force to mass into acceleration, delta x, delta y, delta z will be cancelled on both sides. So finally this total forces of body force and surface force can be equated mass into acceleration. So mass is effectively here now rho, since delta x, delta y, delta z cancel, and acceleration. So we have already seen when we consider the concept of the Eulerian concept, which we have seen here. We are using Eulerian concept in the derivation of this equation. So while considering this Eulerian description, so the acceleration can be written as the local acceleration del u by del t plus the convective acceleration, so del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del z. So this gives the total acceleration in x direction. So that mass into acceleration means rho into del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del z. So this gives the general differential equation of motion in x direction. So final equation is rho gx plus del sigma xx by del x plus del tau yx by del y plus del tau z by del z is equal to rho into del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del z. So this is the general differential equation of motion for fluid in x direction. So from this only we will be deriving other equations like Euler's equation or other kinds of equation. So now this is the equation in x direction, and the general equation of motion in y direction can be written as rho gy plus del tau xy by del x plus del sigma yy by del y plus del tau zy by del z equal to rho into del v by del t plus u into del v by del x plus b into del v by del y plus w into del v by del z, and the general differential equation of motion in z direction can be written as rho into gz plus del tau xz by del x plus del tau yz by del y plus del sigma z by del z is equal to rho into del w by del t plus u into del w by del x plus b into del w by del y plus w into del w by del z. So, where u, v, w are the velocity components in x, y, z direction when we consider the fluid motion in 3 dimension. So, now we got the general differential equation of motion for the fluid in x, y, z direction. So, now from the general differential equation of motion we will be deriving various equations. So, the first case which we will be considering here is the case for inviscid flow. So, the equation is basic equation is Euler's equation. So, here the Euler's equation for inviscid flow based upon the general differential equation of motion we will be deriving. So, Euler's equation is concerned that equation is valid for inviscid or non-viscous flow, that means shearing stresses are 0. So, we have already seen the general equation here, the shearing components are there. So, when we consider the Euler's equation for inviscid flow, that means there is inviscid means no viscous non-viscous flow, so that we do not have to consider the shearing stresses, so that shearing stresses become 0. This actually it is not an exact way, but we can approximate many of our fluid flow like wind flow or air flow or water. We can approximate if the viscosity is small, so that sometimes we can neglect the viscosity and then still this Euler's equation can be utilized in many of the problems. But it is an approximation. We are considering say the viscosity of air or water is small, so that it can be neglected. And then as far as the general equation which we have considered here, general differential equation of motion is concerned, now for Euler's equation or inviscid flow is concerned, the shearing stresses are 0, so that the shearing terms have gone on the left hand side of this equation, and then we have this normal stress component. So, as far as normal stress components are concerned, so if you consider say normal stress component, so it will be generally the pressure which will be acting, so that we can write for the fluid element is concerned with respect to x, y, z direction, we can approximate as minus p is equal to, which is the pressure force, minus p is equal to sigma xx is equal to sigma yy is equal to sigma z. So, here we use the negative, we are putting this as negative, so that component normal stress will be positive. So, now like this we are approximating the normal stress component to the pressure term which is coming upon the fluid. So, minus p is equal to sigma xs is equal to sigma yy is equal to sigma z. So, now after this approximation based upon the general equation which we have already derived here. So, now the shear terms have gone, and the normal stress components with its derivative we are now approximating with respect to the pressure components, so that finally this equation can be put as the general equation of motion for Euler's, so for inviscid flows reduces to like this. So, that the general equation of motion in x direction can be written as rho g x, that is the body force, minus the del p by del x. So, the pressure gradient in the x direction is equal to rho into del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del z, and in y direction we can write rho g y minus del p by del y is equal to rho into del v by del t plus u into del v by del x plus v into del v by del y plus w into del v by del z, and in z direction rho g z minus del p by del z is equal to rho into del w by del t plus u into del w by del x plus v into del w by del y plus w into del w by del z. So, these are the Euler's equation for inviscid flows. As I mentioned, say this air flow or the water flow is concerned, we can sometimes we can neglect the viscosity, and then we can use this Euler's equation, so that the shearing terms are not considered. So, for Euler's equation can be utilized, but it is an approximation. So, this Euler's equation, this name for this equation, this name is given to honor Leonhard Euler, who lived from 1707 to 1783, that is in the 18th century. So in his honor only these equations are named as Euler's equation, and this same equation in x y z direction which we have derived now, we can express as in vector notation as rho g minus del p is equal to rho into del v by del t plus v dot product del v. So here this is the vector notation form of the Euler's equation. So where v is the velocity vectors and g is also with respect to x y z the acceleration vector. So the vector notation can be written like this. So now, as I mentioned, this Euler's equation is one of the fundamental equation of fluid mechanics, even though here we consider the flow as inviscid, but many of the practical cases like water flow or air flow, we can approximate as inviscid and then try to get a solution. The advantage is that here now you can see that these equations are simple, and then we can easily try to get the solution will be much easier if we do not consider the shearing terms here, but it is an approximation. But still this Euler's equation have got lot of applications in practical areas by wherever the fluid viscosity can be neglected or small value of viscosity is there. So based upon this Euler's equation, now we will be deriving another fundamental equation, so called Bernoulli's equation. So this Bernoulli's equation is actually one of the most important or most useful equation in fluid mechanics. It is one of the fundamental equation. So this equation, Bernoulli's equation, can be derived by direct application of the Newton's second law into a fluid particle moving along a streamline. So or we can use the Euler's equation and then derive, or we can also derive from the conservation of energy. So now we will discuss. We have already seen the Euler's equation for inviscid flow. Now based upon the Euler's equation here we will derive the Bernoulli's equation, which is one of the most important equation. So as I mentioned here, so it can be either derived by direct application of the Newton's second law, or we can use the Euler's equation, or we can derive it from the conservation of energy. So as far as Bernoulli's equation is concerned, so it has got some restrictions. So this Bernoulli's equation is derived based upon the assumption that flow is in steady state. So time component is not there. Flow is a steady state and density is constant, so that fluid can be considered as incompressible. And then of course we also put the assumption that fluid is inviscid, and so that the friction losses are negligible. So these assumptions, actually many of the practical problems it will be difficult to apply, but certain times, certain cases we can approximate the flow is, even though say the viscosity is to be considered, but wherever, as I mentioned, whenever water is concerned, since its viscosity is small, or air flow is concerned, viscosity is small, we can use this Bernoulli's equation. So the assumptions are flow is steady, density is constant, and inviscid flow. So actually this Bernoulli's equation, it relates the states at 2 points along a single streamline. So whenever there is a fluid flow is there, so if you consider a fluid flow here in a channel like this, so here say we consider two section here 1 and 2 and fluid is flowing this direction. So this Bernoulli's equation is it gives a relation between 2 points. If you consider this point here and this point 1 and 2, it along a streamline, if you consider a streamline like this, so the Bernoulli's equation is an expression for it gives the states, what is the states between this position and the first position and second position. So that is what the Bernoulli's equation states. So now we will derive here the Bernoulli's equation based upon the Euler's equation, which we have already seen earlier. So from Euler's equation, at steady state the equation, so we have already seen earlier here the Euler's equation for the with respect to vector notation. So if we consider the flow as in a steady state condition, so then we can write rho g bar is minus del p is equal to rho v bar dot del v. So this is the Euler's equation at steady state. So now to get the Bernoulli's equation, we will be integrating this equation along some arbitrary streamline. So before the integration, so the acceleration due to gravity we can write as g bar can be written as with respect to the normal direction minus g del z. So and then also this other term del dot v. So v dot del v bar, this right hand side of the equation, the steady state equation, Euler's equation can be written as can be approximated in using the vector notation in mathematics as half del v dot v minus v cross v del cross v. So this is from the vector algebra, the mathematics vector product and dot product, we can get this equation. And now Euler's equation finally becomes rho g del z minus del p is equal to rho by 2 del v dot v minus rho v bar cross del cross v. So this we can rearrange as del p by rho plus half del v square plus g del z, and that is equal to v cross del cross v. So now we are approximating the Euler's equation to derive the Bernoulli's equation. So now say let us consider a streamline like this as shown in this figure here. So if you take the dot product of each term with a differential length ds along a streamline as shown here, this is streamline. So that way the equation becomes del p by rho del dot ds plus half del v square ds plus rho del z ds is equal to v cross del cross v ds. So now this ds has a direction along the streamline. So here the direction is shown here, and ds and v are parallel. So since the streamlines are derived like that, so that we can write also v cross del cross v is perpendicular to v bar, so that we can write v cross del cross v dot ds is equal to 0. And then this ds can be this ds in the previous figure, here this ds, this vector can be splitted into say here it can be splitted as dxi plus dyj plus dzk. So that finally we can write del p dot ds is equal, and also del p ds can be written as del p by del x dx plus del p by del y dy plus del p by del z dz, that is dp. So that finally after using all these approximations, the Euler's equation in steady state become dp by rho plus half dv square g dz is equal to 0. So after using all these approximations put forward here in the slides, finally we get this dp by rho plus half dv square plus g dz is equal to 0. So now along the streamline as discussed here, we will integrate so that integral d p by rho plus v square by 2 plus g z is equal to constant. So finally this gives the Bernoulli's equation. So the Bernoulli's equation is actually here three terms. One is say with respect to pressure, other one is the velocity with respect to velocity square, and the position head g z with respect to z. So this is the integral form of, this is the general Bernoulli's equation. So as we have seen, this is valid for incompressible and inviscid fluid. Actually we can, this general equation, since rho term is there, so this is valid for compressible and incompressible viscous inviscid fluid. This is valid for compressible and incompressible viscous fluid. So that we can write p by rho g plus v square by 2g plus z is equal to constant. And now between two sections, if we consider two sections as we have seen here in the previous here, if we consider this section 2 and section 1 and section 2, then finally we can write p1 by gamma plus V1 square by 2G is equal to Z plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z1 Z2. So, here this, if we consider in this figure here, this is the datum. So, and here this is Z1 the position head, this is Z2 the position head. So that finally with respect to Bernoulli's equation, and P1 is the pressure here, V1 is the pressure velocity here, and P2 is the pressure here, and V2 is the velocity on the section 2. So, finally the equation become P1 by gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2, where gamma is the specific weight of the liquid. So, this is the general equation when we consider between two sections. So, the Bernoulli's equation, actually, even though we derived the equation earlier for a general one, but it is restricted to inviscid flow or non-viscous flow, and it is in steady state, and the general application is for incompressible flow and flow along a streamline. So, these are some of the restrictions as far as the Bernoulli's equation is concerned. So, here the equation is applicable for inviscid flow, since from the Euler's equation we are derived, and steady state only we are considered. So, it is generally applicable to incompressible flow, and we generally take a streamline and then flow along a streamline is the equation is derived. So, here in the previous slide you can see here, there are three terms. One is say P1 by gamma, that is actually so called the pressure head, and then the second one is V1 square by 2G, which is so called velocity head, and then Z1 and Z2, which is considered here, that is the datum head. So, the Bernoulli's equation includes three terms: the pressure head, velocity head term, and datum head. So, now with respect to this, we can see that the work done on a particle by all forces acting on the particle is equal to the change of kinetic energy of the particle. So, if we consider for the particle which we are on the streamline which we are considering, so that we with respect to the equation we can say that the work done on a particle by all forces acting on the particle is equal to the change of kinetic energy of the particle. So, now also the Bernoulli's equation can be derived from the, as we have seen, we have derived now the Bernoulli's equation based upon the Euler's equation for the inviscid flow, but Bernoulli's equation can be also derived from the basic Newton's second law, or also we can derive from the conservation of energy. So, from the conservation of energy for the system which we are considering, say as we have seen in this figure, for here we can see that the energy, like pressure energy per unit weight plus the kinetic energy per unit weight plus the potential energy per unit weight is equal to total energy per unit weight. So, as per the conservation of energy, this total energy is conserved, so that the pressure, the energy per unit weight due to pressure, kinetic or potential, that should be considered. So, this gives the total energy per unit weight. So, total energy in the system does not change, or total head loss does not change. So, since the total energy is not changing, we can say that the total head also does not change. So, that we can write from this the energy conservation, we can write P by rho g plus U square by 2G plus Z is equal to constant. So, this is coming from this basic energy equation. So, the same equation we are getting from the conservation of energy principle also. So, if you consider say a flow in a channel or a flow in a pipe like this, so if you consider 2 points as shown in this slide here, 2 points joined by a streamline. So, the total energy per unit weight at 1 is equal to total energy per unit weight at 2. So, or total head at 1 is equal to total head at 2. So, that is why we are getting P1 by rho g plus U1 square by 2G plus Z1 is equal to P2 by rho g plus U2 square by 2G plus Z1 for this section 1 and section 2 which we considered here. So, finally, the total energy per unit weight is equal to total energy per unit weight at 2 plus if there is any loss. So in case if there is in the previous, with respect to previous figure, if there is a loss per unit weight, that also we have to consider. So that is considered here as H, and in case between section 1 to section 2, if any work is done, that also to be considered, that is W. So work done per unit weight minus energy supplied per unit weight. So if we consider all the aspects, then the equation becomes like this P1. So with respect to this previous figure, if we consider the work inside between section 1 and 2, and also any loss of energy between section 1 and 2, and then any energy supply also considered, then we can write the general equation as P1 by rho g plus U1 square by 2g plus Z1 is equal to P2 by rho g plus U2 square by 2g plus Z2 plus H plus W minus Q. So this is the generalized equation when we consider a real system. So the earlier equation which we have considered is for the only pressure head, velocity head and datum head are considered as derived here. But when we consider any real system, there can be loss of energy, or there can be energy supplied, or there can be work done. So all this will be considered as shown in this the general equation. So now, as we have already seen, the equation is applicable across the streamline also if the flow is irrotational. So we have already seen we have derived the equation for flow along for a the equation is derived for streamlines along a streamline, but it can be also applied across streamlines if the flow is irrotational. We have already seen what is rotational from the irrotational flow. For the case of rotational flow, we can say that the Bernoulli's equation is also applicable for across the streamline. And some of the practical applications, the same, if the restriction of frictionless flow can be considered, then we can accommodate by introducing a loss of energy term and restriction of rotational flow, as we have seen here. So and we can apply many of the cases which we will be discussing later. So some of the important applications of Bernoulli's equation we will be discussing later. So Bernoulli's equation, as we have seen, it is a special case of general energy equation. So general energy equation which we have seen here, so it is a special case of the general energy equation. So now with respect to this, we will be discussing some of the applications of Bernoulli's equation. So say some of the things which we should always remember before using this Bernoulli's equation, it may be applied without much error for unsteady flow, also with gradually changing condition. We have already derived the equation for steady state condition, but if the variation is very gradual, then still sometimes we can use this Bernoulli's equation for unsteady flow with gradually changing condition. And also for flow of gases where the change in pressure is a small fraction of the absolute pressure, we can treat as incompressible, and then can be considered the Bernoulli's equation. And when all streamlines originate from a reservoir where the energy constant is everywhere the same, the constant integration does not change from one streamline to another, so that this case also we can consider. So these are some of the cases which we can consider the Bernoulli's equation. Further application we will be discussing later. So before closing today's say, just we will also see a simple example here. So Bernoulli's equation, a small example is discussed here, will be discussed here. So here a fluid of density rho is equal to 980 kilogram per meter cube is flowing steadily through a tube. Here you can see a tube, liquid is flowing through this tube, and the diameters at section 1 is 10 centimeter and section 2 it is 12 centimeter, and gauge pressure at section 1 is 260 kilonewton per meter square, and velocity here at section 1 is U1 is equal to 5 meter per second. We want to find P2. So here just this simple example shows how the Bernoulli's equation can be applied. So here we can see that there is a tube, and then varying, the diameter is varying, and the liquid is flowing through, and the two sections we are considered, and at one section the velocity is known, the pressure is known, and other section both section the diameters are known. We want to find the pressure at section 2. So that is what we want to find in this particular problem, and the pressure at section 1 is given as 260 kilonewton kilonewton per meter square. So here we will be using the Bernoulli's equation and also the continuity equation. So we will apply the Bernoulli's equation along streamline joining 1 and 2. So here we are, as shown in this figure, the tube is assumed to be horizontal, so that is Z1 is equal to Z2. So the general equation we can write with respect to Bernoulli's equation, P2 plus rho by 2 U2 square is equal to P1 plus rho by 2 U1 square. So you can see here section 1 and 2 we are equating, say, the pressure head and the velocity head. Z1 is equal to Z2, so datum head is not to be considered. So section 1, section 2, so that P2 plus rho by 2 U2 square is equal to P1 plus rho by 2 U1 square, where U is the velocity, P is the pressure. And now the velocity at section 1 is already known, U1 is equal to 5 meter per second, but U2 is not known, but so that we can use the continuity equation. So from the continuity equation we can write A1 U1 is equal to A2 U2, so that we can get U2. So U2 is equal to A1 U1 by A2. So the diameters D1 is 10 centimeter and diameter D2 is 12 centimeter, so that we can write U2 is equal to D1 square by D2 square into U1, and if you substitute all the values here, so we will get the velocity U2 is equal to 3.47 meter per second. And then once the velocity U2 is known, we will substitute back to this equation here, the Bernoulli's equation here, so that P2 is equal to P1 plus rho by 2 U1 square minus U2 square. So in this equation all the values U1, U2 and P1 are known, so that we can find P2. So P2 is equal to 266.35 kilonewton per meter square, and you can see that when the velocity is decreased from 5 meter per second to 3.47 meter per second, pressure is increased from 260 kilonewton per meter square to 266.35 kilonewton per meter square. So this problem shows a simple case of the application of the Bernoulli's equation. So in a very similar way, large number of problems, practical problems can be solved using the Bernoulli's equation. So further applications of the Bernoulli's equation will be discussed later.